Thanks for joining us today. Let's begin with a quick introduction about myself and Raheleh. So my name is Hicham. I lead the data engineering insights team in Pelmorex. I've been working in Pelmorex since 2009. I started as a software engineer working on developing backend solutions for the weather warning system. I then joined the Android team and worked on developing the weather network Android app for phone, tablet, and TV. Then I worked on developing chatbots for Google Assistants and Facebook Messenger. A few years ago, I joined the Data Insights team, who developed different insights-driven solutions for the B2B. So over to you, Raheleh.
Yeah, thank you, Hicham. Good morning, everyone. I'm really excited to be here today to share our experience and expertise about the challenges and learnings of machine learning at a scale. So my background is mechanical engineering. I received my PhD at mechanical engineering at University of Waterloo. And then I was working as the postdoctoral fellow at the University of Toronto, where I focused on working with both machine learning and deep learning algorithm to enhance indoor air quality. So by leveraging both supervised and unsupervised methods, I was able to create models to predict peak pollutant concentrations and also source of this pollutant. So by this, we were able to activate the ventilation system in automatic way to increase and enhance indoor air quality in cost-effective way. After that, I was looking to apply my knowledge and experience in both environmental engineering, mechanical engineering, and like the machine learning. And this led me to join Pelmorex as the data science. And now I'm currently in the Weather Insight Platform project. So I will, at high level, I will explain about Pelmorex. Pelmorex was founded in 1989, and it's since then has become international weather and data management company, and it owns various popular brand weather companies such as the Weather Network, Meteo Media, Il Tempios, Clima, Otempo, and Weather Source. With the collaboration with Weather Source, we have access to the global on-point weather data. It can vary from climatology data, historical, and also forecast. And our forecast data is among the most accurate data that we get from ECMWF that cover every time scales from hourly days, week, and months. And also every day we have access to updated the next 14 days and next 14 2 days forecast weather data. Pelmorex data team also consists of more than 50 data scientists, data engineers, and full-stack developers who specialize in solving weather-centric challenges. And with these resources and expertise, we have initiated a project to uncover weather-related insights and their impact on cells, which is we called it Weather Insight Platform, or WIP. So now I will go through the high-level overview of what is WIP. So we start by, we are talking about WIP because this is the project that we had challenges associated with implementing machine learning at a scale. So we begin by leveraging the data for visitation, transactional, or sales at SKU level. So it means that like whatever data related to visitation, transaction, and sales at a specific product and a specific store we have, we can correlate with weather data that we get from Weather Source. And these weather data are not just raw data. We are doing feature engineering to determine and define new features. For example, the anomaly features, if the temperature is higher than normal, or the precipitation anomalies, or the panic buying features. Those features that are related to the panic behavior of people. And after that, we conduct in-depth analysis to determine the local on-point relation of weather with sales data. For this, we are doing like correlation analysis and also historical analysis that in like further slides, I will go through them in more detail. Based on these results, we have kind of these maps that we called it the breadth and depth of the analysis. By breadth, we mean that like how many stores are affected by that specific weather conditions, like the sales increase or decrease. And by depth is what's the percentage of that affection, like what, like at a specific weather conditions, if the sales of this specific product like increase by 10% or decrease. So then we can determine the subset of products that are affected actually by specific weather conditions. And every time, like in this project, we are talking about on-point weather data and in a specific location, because like people behave differently at the same weather conditions at different locations. Like at a specific temperature categories, like people behave differently when they live in Toronto or they live in Florida. So that's why our focus in like on-point weather data, and that's where part of our complexity of model comes, because for each location we are like dealing with specific weather conditions. And lastly, when we select those product and stores that are affected by weather, we start training our machine learning model based on like specific store and product, and based on different features that we have, such as the calendar features, sales features, and those raw weather features, and also the new weather features that are defined by our team. When we train model, it's time to prediction. So every day we have access to the new updated weather data for the next 14 days. So every day we need to update our prediction to determine the next 14 days sales based on the weather data that we have. And with the machine learning model that we have, we also have access, we also can determine those weather features that are important in our prediction. For example, for this specific product, we realized that temperature is among those features that are really important and contribute to 9% of those features. And after that, it's precipitation and sunshine. So that's why it shows the importance of weather, and we need to update this prediction every day. We also have climatological data that is the average of, that can be defined as the average of the historical weather data for the past 15 years. So when by considering this climatological weather data, we can get the sense of what's going on the next year. Although this climatological weather data is not accurate and we cannot like use them completely as the forecast, but the client can get the idea of what's going on for the next year. Till now, you get the idea about the scalability of our model. So we are working with various clients, and also we are working with one of the top 3 biggest retailers in the world, with having thousands of stores and thousands of products. With this in mind, we ended up to having millions of models that we need to train regularly. So these millions of models, they need the computational resources is significantly increasing, and they need various complexity management, and also in the back end we have substantial infrastructure for them. The question arises here is, do we really need to train model based on store and product specifically? Or maybe we can just focus on the product and train model for all of the stores. So yes, the answer is yes, we can actually train model based on like all of the stores as well. And it's actually more simpler than we have, although we need to consider like some other features that we consider for the store definition. And also we can generalize it for like across all of the stores. However, we don't have the granular store product insights anymore. So when we train model for each specific store and product, we can like determine the insights for each granular store specific insights. By training a separate model for each store and each product, we can capture the unique dynamic and behavior specifics to each individual store and product. For example, as I mentioned, in one location, the temperature may be really more important than like precipitation. But in another location, precipitation is actually getting more important. So by training our model in store and product combination at this granularity level, we can actually realize all of these insights of weather related actually much better. And the second advantages is we can actually have customized model parameters for fine tuning the model. So for each store and product, we have like different model, and these weather conditions are like considered actually differently in each model. So that's why like based on between these choices, we ended up to using to train model based on store and product combination, but we still have the issues of we need to train millions of model. So that's why before training our model, we ended up to doing like some algorithm to reduce the number of products or stores based on if they're affected by weather. So if we realize that some products are not affected by weather at all, it's not making sense. It doesn't make sense to run those models actually. So that's why at first we need some correlation analysis to realize that if the cells of a specific product are affected actually by a specific weather conditions. And we are doing this correlation analysis on monthly basis because we want to consider and determine any seasonality effect. If the sales of the product increase in summer and decrease in winter, it's mainly because of the seasonality effect. It cannot like based on the temperature effect. So that's why for each month we calculate the correlation of the sales of the product and also the weather conditions to determine if we have like highly correlated, either it can be positive or negative, it doesn't matter, because we are working with those products that the specific weather condition increase sales for them or decrease sales for them. So based on this analysis, we determine the subset of those products that are affected by weather. And the previous correlation is mainly considered those linear correlation. For example, if temperature goes up, the sales of a specific product goes up. So we cannot determine those specific ranges that leads to increase or decrease sales. For example, in this plot, you can see the percentage change of like sales of a specific product at different weather conditions, at different temperature conditions when we compare with the average sales of that season. So we see that when temperature is between 55 to 70, the sales is actually increasing more. However, at lower temperature and higher temperature, we have lower sales. So these kind of analysis are not captured actually by the previous correlation analysis. So that's why we are doing historical insights here. For each weather categories such as precipitation, temperature category, wind category, and cloud condition, we define their specific weather conditions, and we determine the distribution of cells through each weather conditions, and we compare them to each other. All of these are passed through the statistical analysis, All of these are passed through the statistical analysis to realize that if the difference between these cells distributions are just happening by chance, or if it is something that we can partially explain by weather conditions. So, for example, these results are passed through the statistical test, and the p-value is, by choosing the p-value of 0.05, we are 95% confidence that when temperature is between 55 to 70, the cells of this product increase. So by doing actually this analysis for every store and every product, we determine like those weather conditions that increase or decrease cells. For example, here it shows like the results for all of the stores for one product, and we see that like at northern part of the US, at lower temperature, the cells of like that specific product increases, and as we go like to the southern part of the US, we see that like the cells of that specific product increases even at higher temperature. So that's why, that's one reason shows that why we need to like use localized weather data. So till now, we ended up to having that we have, although we separate those models, although we separate those products that are affected by weather, we still have millions of models to train. Based on the client that we are working on, we receive those live data on weekly basis, monthly basis, or quarterly. And whenever we receive data, we need to retrain everything again and monitor the performance of our model. But at the end of the day, we need to predict actually every day, because like every day, the forecast weather data is getting updated, and we need actually updated prediction. So that's why like it doesn't matter if we train on weekly, monthly, or quarterly time frame, but we need to predict every day. So in overall, we are looking for a model that is really efficient in training, and also we really want fast prediction, but at the same time, we want to maintain the accuracy actually at the high level. And another important criteria for us is we really don't want those black box model, because those weather features are really important for us, and we really want to see that what are those weather features that increase or decrease cells for the next 14 days. So that's why, by considering all of these criteria, we ended up to training our models based on like XGBoost model that like meet all of these criteria. So I'm not going through the detail of those hyperparameters that we use for XGBoost, because that one is really depends on the client and also the data that we have. However, for the hyperparameter tuning, we ended up to trying use 3 methods: the random search CV, the grid search CV, and Bayesian optimizations. And after considering all of this, and based on the data that we have, we ended up to actually using the random search CV. Because the reason is like it randomly select all of the hyperparameter combinations, and we can tune more parameters in wider range of the values with fewer iteration. And when we did experimentations and compare all of these 3 approaches with each other, based on the size of the data that we have, we actually got desirable performance. So till now, I explained about the overall project that we are doing and why we need to like run millions of model in regular basis, and why we need to predict like every day. So I will pass to Hicham, so he will explain more about what is going on the back end and infrastructure.
All right, thank you very much, Raheleh. So I'm going to take you over the following slides through the journey my team and I went through to optimize and scale our machine learning capability from thousands to millions of models. But first, let's begin by taking a look at what composes the training of our machine learning model. So in order to keep the training focused on what it's supposed to do, which is training the model, but also optimize for the training time, we managed to handle all the heavy lifting in terms of processing and features preparation in upstream pipelines, hence the data preparation step. So this way, once we get to train the model, all the features that the model needs are already there, mainly to be picked by the model to train, but also for future inspections if needed. So with that, the training gets the ready-to-use data for a specific model, splits it in tests and training data, fine-tunes and optimizes for the hyperparameters, and then get the training started using XGBoost model, and finally evaluate the model and push it to GCS. And that whole process from the split to the push of the model, that whole process takes less than a minute. Next slide, Raheleh. So when we knew that the training process was taking less than a minute, we said to ourselves, well, that's great. Let's then put that training process in a container, have a cluster or whatever allows to manage hundreds of machines in order to distribute the training across those machines. And we should be just fine to easily scale to thousands of models. But unfortunately, the reality was different, and I will tell you why in a second. So first, let's take a look at our very first version of the architecture we went with. That architecture uses Apache Airflow to schedule the training of batches of hundreds of models, and Cloud AI as the platform to run the training across hundreds of instances in a way that each instance is dedicated to one model at once. So, of course, that architecture allowed us to reach 700 models in about 60 minutes, but couldn't keep up with the demand from the product team to train thousands of models in less than an hour. And the reason why we couldn't reach 1,000 model capacity under an hour is because in reality, while the training of a single model from the start to the end takes less than a minute, it turns out each instance dedicated to train a single model takes time to spin up, get the Docker image, and run it before it becomes fully ready to train a model. So in total, it takes a few minutes to start the instance and another few minutes to stop it to be able to make it again available to train another model. So in reality, it takes up to 5 minutes to train a model. Also, it turns out Airflow was just not suitable to manage hundreds of training jobs, which became for us a single point of failure. Once it fails, the whole process of training the models becomes unstable and fails with it. Next slide, Raheleh. So since then, we knew that in order for us to reach a 10,000 model capacity or higher, which was the target back then 2 years ago, we had to solve for two things. One, avoid the one single point of failure caused by Airflow. Two, cut as much as possible the overhead time caused by the spin up and shutdown of the instances. So we then came up with this architecture that uses Dataflow to take the load out from Apache Airflow into multiple workers. That Dataflow scales up and down dynamically based on the load. So Dataflow pipeline became for us some sort of a scalable training orchestrator. It reads the model's IDs to train from BigQuery and triggers the training of each model by firing a post request that sends the model ID to the training service. And the training of the models happens then on the training service, and this ladder takes care of fetching the training data from BigQuery based on the model ID, runs the training, and saves the model on GCS. So this architecture did indeed solve for the two issues mentioned previously. As for the single point of failure, it takes advantage of the fault tolerance of Dataflow to distribute the training over multiple workers running under multiple VMs. So when a VM becomes unhealthy, it doesn't cause the entire job to fail. And we also put in place a retry mechanism in case of whatever reason the training fails. As for the overhead time of starting and shutting down the instances to distribute the training load, this architecture takes advantage of Cloud Run dynamic and fast scaling to not only scale with additional instances, but also reuse the existing instances to train more than a model at the same time, or train the next one without the need to shut down the instance. So we also achieved with this architecture a significant performance improvements and used it to train dozens of thousands of models. However, the product we support has, of course, evolved, and the data sets we use have also evolved with it, which can start putting pressure on the system to train for hundreds of thousands of models. And with that, new problems start to emerge. One is yet again the performance, and the other is related to costs that start to explode. Next slide. So indeed, we just couldn't wait dozens of hours and pay thousands of dollars to train hundreds of thousands of models. And therefore, we introduced a couple of improvements to the previous architecture. Since each model to train requires to fetch the training data from BigQuery, that caused a significant spike in BigQuery costs. And furthermore, each query takes time to run, and that adds to the training time. So because of that, we decided then to fetch the training data of all the models only once at the level of the data flow pipeline, break down that data by model, and then send the data of each model in the post request along with its model ID to the training service. I think it's worth also mentioning that we could have also done this with PubSub, but that turns out to be less performant when we tested it. So with that, the training service no longer needs to fetch the training data from anywhere because it simply comes within the HTTP call. And that indeed gave us the ability to train multiple hundreds of thousands of models about 8 times faster and cheaper than before. However, we quickly start seeing the need of training even millions of models on the horizon, and we knew we needed to do more to support that. Next slide. So we learned from the previous architecture 2 things. One, training data sent over HTTP takes time to transfer. And 2, data flow workers scale up much faster than Cloud Run, which floods the training service with a high number of training requests it can't quickly catch up with, which trigger the retry mechanism meant for us to protect us against failure, but now adds up to the load with even more requests. So we knew that in order for us to achieve much better performance, we needed something that minimizes the data transfer over the network, but also reduces failures to avoid too many retries. And one way to achieve that was by packaging the training process within Dataflow itself and fully benefit from the dynamic work rebalancing that makes Dataflow one of the fastest load distribution and resource utilization out there. So in fact, that allowed us to train 1.3 million models in less than 6 hours. Of course, my team and I haven't given up on the scale up and optimization, and much more is to come. Next slide. So we thought it worth also mentioning that one of the frameworks we looked into in this journey was Ray. Some of you may know or even use Ray, and if you don't, I would highly recommend you to check it out. It's a great AI at scale framework. However, the reason why we didn't went with it for our solution is the startup time overhead and sometimes some workload balance issues we have noticed in our benchmark comparing our solution performance and resource utilization against Ray. The 2 diagrams show the CPU utilization of the instances used in the training. we have seen that it takes time with Ray to balance up the load across multiple machines, and sometimes some instances are not using the available resources to their full potential. So that's pretty much it about the engineering and the scale and its challenges and lesson we learned with it that we love to share with you. And I think we are open to questions now.
Yeah, so one question here is, do you have data coverage outside of the US? If so, do you find differences in data quality between countries or differences in what feature tend to be important, etc.? Yes, we have actually weather data on global, actually, like for every latitude and
Raheleh, I think, can you hear me?
Yes. Yes, Hicham.
For some reason, I can't hear you. I don't know if
can
other
anyone hear
people
me?
can hear me.
Yeah.
Okay. Yeah, sorry about that. But I can't hear you, Raheleh. I'm not sure if the audience can hear you as well.
Yeah, they mentioned they can hear. Okay.
Okay, great.
So we have actually access to on-point location weather data globally. So for each latitude and longitude, we have API and we can actually get weather data. So there is no issue for that. But we have raw weather data. So what we are doing we are doing feature engineering to extract more weather related feature based on this regular weather data that we have, like temperature, precipitation, and those things. So this, and I think this answers your question about like the weather data, but the sales data, I can say that like the sales data is actually not in the control of ourselves because it's mainly dependent on the client that we are working with them. So we are working with different clients, retailers, restaurants, and groceries. And they provide us sales data for their product. Like the retailers can provide us data for the electric department or whatever department that they have, or the restaurants for all of the menu item that they have in their menu, and also the grocery one. So I think I answered your question, but let me know if like you have any other questions then. So not sure if it matters, but I see a note as well.
I see someone asking about why don't we train the models on single machine simultaneously. Of course, we needed multiple machines like to distribute the load. And yeah, that's kind of the point also we try to solve for, which is kind of how can we also, take, full advantage of each instance that exists to also kind of push it to train, to do the training in two ways. Actually, if there are any resources available on that machine to also like go on and train more than a model at once. Second is keep the machine alive. So to optimize for creating once again the instance or shut it down. For Ray, I provided like the reason at the end. Basically, it takes some time to kind of catch up with the load, and every single minute kind of in that process kind of becomes for us kind of a big deal. That's why like that flow and its work rebalancing algorithms help a lot in orchestrating multiple machines pretty fast.
Yeah, thank you. So another question is, sales are usually driven by number of customers, and number of customers is driven by their motivation to go to, which is affected by weather data. By directly link sales with weather data, how do you deal with correlation versus causation problem? Yeah, so that's a really good question. So we have actually we have both visitation and also sales data. So for some clients, they gave us like both of them. So then when we have actually both of them, we can realize actually if the sales is like only correlated like by the visitation data, or if it's just the product sales. For example, for one of the clients that we have is when we did correlation analysis between the visitation and also the product, we realized that for some specific months of the year, we didn't actually see the highly correlated with sales and visitation. And when we did the statistical analysis on those products, we realized that those products are mainly affected by weather conditions. There may be some other conditions that affect, like there should be maybe the event or the promotion or those things. But based on the statistical analysis and based on the data that we had, we actually saw some signals from weather as well. So that's how we handle actually this correlation.
Thanks, Raheleh. There is also another question about BigQuery. Someone asked, doesn't your BigQuery API call become a single point of failure if you are fetching all models details from it at once? Not at all, because BigQuery is by nature a scalable, available solution. So we took advantage of its kind of high level of availability. And once we get the data all in, we don't kind of manage it in any kind of single instance or point of failure for us. It's become a distributed in-memory data that kind of data flow takes care of, forwarded to the right kind of worker dedicated to train the model. Hope that answered your question, your concern.
Yeah, thanks. So another one is, what type of products are being considered here? So we are actually working with three main clients, like the retailers, restaurant, and grocery, and the products are like determined by them. So like that's one side of our project, and another one is like we are working with visitation and the total transaction. So this visitation and total transaction doesn't include any granularity of the product. And also the next one is, do you retrain on all historical data or choose a subset for weekly, monthly, quarterly training? So based on based on the client, we receive updated data like in a time and manner way. Like we have clients that every quarter they updated us new data, but some of them maybe they update like on weekly and monthly. But whenever we receive new data, we go and like based on like the behavior of the data, based on like everything, we determined like the subset of time period that we need to retrain everything. There are some products that are highly affected by that were highly affected by COVID years. So that's why like we need to actually customize our model and determine that what time period we need to retrain. So for some of them, we ended up to using like data from 2021 till now, but for some others, we realized that COVID years didn't actually affect the sales of the product. So we have actually more flexibility to use more data, but we usually use the last 3 to 5 years of data to train our model. So I think this is yours, Hicham. How to improve the prediction speed when the model is deployed on production and we have to serve millions of clients?
Yeah, so just for the sake of time, we couldn't cover the prediction, architecture. Basically, it's quite the same, right? What was more easy with the prediction is it takes less time than the training, right? So that's why we were able to generate in a daily basis predictions in kind of about an hour or two. So we haven't seen kind of issues. And as I mentioned, we continue kind of optimizing for the performance as we move along. So we have kind of ran that architecture for up to 2 millions for now. We have kind of full confidence that it can handle much more than that. But of course, we are keeping an eye as the product is evolving.
So one question is, how do you approach unanticipated data formats types in your input feature pipeline? So that's a really good question. And this is actually one of the main challenge actually, because like it depends on the client. So what we are doing is like whatever data client like give us, we update based on the format that our pipeline actually requires. So, and then like start from there. But also what we are doing and what we are planning is we need to actually define some specific formats, and then the clients needs to update their format, update their data based on that format. And then like everything is from that step is everything is going to be automated.
So does anyone else have any other questions? Hopefully we've covered all the questions you posted in the chat, but feel free if you still have any other questions.
So one question is about following up retraining methodology, and how do we validate if the retrained model performs as well or better than the previous model on older as well as the new data. So this is something that we are working on that, but what we are doing is we save actually all of the models, and we determine that we monitor the performance of those models over time. And but usually when we have, in most of the time, when we have like newer data, then we have actually more access to the more recent data, and like it what we can say is like the new prediction can affect mostly by the recent data that we have. Like, for example, when the client update us quarterly data, because we have the last quarter data, the prediction is, although sometimes the accuracy of the model may drop, but because we have recent data, the prediction is getting actually more accurate. So that's how we handle those ones. And we always use the recent train model, but this is something that we are working on to see that in cases that the accuracy of the model significantly drop, maybe we can roll back and use the previous model that we trained.
So next question, what exactly changed in 1 minute model to reduce cost and runtime? I hope I understand the question correctly, but please, comment in the chat. So the model that kind of was taken about 1 minute to train hasn't drastically changed. So it was always continuing kind of about 1 minute. But what has changed is more kind of the infrastructure or the architecture that needed kind of to evolve to be able to train for up to millions of models within a very reasonable amount of time, so within kind of hours. So as the product grows, as I mentioned, like the data set grows, meaning like we kind of need to cover for more locations, more stores, and more kind of product categories. That translate for us into much more number of models to train. And that's why like early versions that I covered in very first like slides were not very suitable to really keep up with the demand of training much more models. So model 1 minute remain kind of the same, but more the architecture that has evolved to provide a better support.
Hicham, there is another question about what exactly changed in 1 million model to reduce cost and runtime.
Yeah, so that's the question I kind of just tried to provide some details about. I hope I've answered and provide some better clarity now. And next question, how Ray helps. So for us, Ray didn't really help. So basically, we experimented with it to see if it could have helped like run the training process much faster and also cost-wise. But when we compared, the matrix of those, benchmarks, comparing them to the, solutions we've developed with Dataflow, we saw that kind of it's performing actually less and costs also more because of multiple kind of instances that sometimes like we need to run much more compared to Dataflow. And for a longer time, because time kind of costs also more costs. But it's a great framework. It just like for our kind of use case, it didn't help.
So is there any questions that we missed or?
Yeah, you don't, because in terms of performance, we saw Dataflow kind of providing much better results. Again, you can check that out for more details if you want. You also to their work rebalancing algorithm that has been kind of fine-tuned over the past years, that kind of allow separation between the workers and the data flow backend service. So that backend service kind of keep an eye on what's going on and kind of scale up and down much faster to keep up with the load.
So another question is, did you have any issue with imbalanced data set? How was the performance of the model in anomaly forecasting? So just for the clarification, what we are doing is we are doing the regression analysis. We are predicting the sales for the next 14 days, 42 days, or the next year. So everything is just the regression analysis based on the sales data that the client actually provides us, and also based on the weather data that we have. So this is just regression analysis. And about the anomaly forecasting, is we have historical weather data. And I can maybe talk about temperature here, that has it's making more sense. We have temperature for the last 15 years for all of the climatology and historical weather data. And for each specific day, we determine, our algorithm shows that if that temperature is categorized among the anomaly ones or just the regular one. For example, maybe today, the temperature, 12th of June, we see that temperature is 5 degrees. So 5 degrees for 12th of June at Toronto area is maybe categorized as anomaly, because in the last 15 years, we've never seen such a cold temperature like at this specific day. But it doesn't mean that 5 degree is always anomaly, because we can have so many days with 5 degrees, but it's not 12th of June. So that's basically it, and how we determine these anomalies. And there are various ways to determining those anomalies. One way is we can do the statistical analysis to determine the maybe top 2 or 3 percentile of the data, and also lower 2 or 3 percentile of the data, to determine that if that specific temperature is categorized between anomalies or not. Or maybe we can compare with the climatology data that we have. So we have we feature engineering all of this for all of the temperature, precipitation, snowfall, solar radiation, or those other features that are maybe it's not commonly used by companies, but these are something that we realized their effect on their sales. So I hope I answered your question.
All right. No more questions?
Yeah.
Are you also tracking online versus store things? I think this is for you, Raheleh.
Yeah, so we are using two main data sets. One of them is a store purchase, these are the store sales, and also we are working with e-commerce data as well. For some of the clients, they provide us e-commerce data, and based on the locations that they ship products to, we determine the weather conditions, and we realize that in each location, what are the effect of a specific weather, and if those weather conditions really affect sales. So yes, in summary, we handle both of them.
So someone asking, okay, what was the main shortfall of Airflow? So the main shortfall is orchestrating really hundreds of training jobs, because it needs to keep track of what has started, what's ongoing, what has finished, to then schedule another batch of hundreds of jobs, and then monitor them as they are happening. So we have seen that that back and forth monitoring between Airflow and the AI platform that we used back then to train models on multiple instances, we have seen that was really kind of becoming some sort of unstable as it keeps kind of managing hundreds of jobs. So that's why Kinfo managed to keep Airflow only scheduling the data flow pipeline, and then the data flow pipeline has better kind of fault tolerance capability. Whenever something fails, it just like put it off and kind of spin up another worker instead. And also, as I mentioned before, we add to on top of that kind of a retry mechanism just in case of something wrong happens, and we can kind of afford doing a retry, an automatic retry in a later time.
What climate data set do you use? So can you explain more about the questions? But the weather data that we have is, we have access to both ECMWF and GFS weather data, and both of them like covered on point every latitude and longitude for on point global. So these are the data set that we have access, and like it consider like all of the climate that we have, but I'm not sure if I understand your question actually correctly. Okay, is there any other questions or? Yeah, okay, thank you all.
Right.
Yeah, thank you
You
all
so
for
much.
participating at this session. Yeah.
Thank you so much, everyone. I hope that was kind of insightful to all of you. And yeah, have a good day.
Yeah.
Thanks, everyone. Bye.
Bye.